All right, so let's move into six. So as I was saying, the maximum population is 203,380. And in what year did this max population occur? That's part D. That would be 31.21 years. So 31 years, so that's going to be 2001. Okay. Now let's look a bit closer. This is the same model, but we want to talk about a little bit further into this question of maxes and mins and generally what we call extreme values. And the phrase to remember here is that the extreme values depend on the interval on which we are looking for the extreme values. So let's find the maximum and minimum values of this function on each of the following intervals. And you're going to see that the maxes and mins will change depending on the interval. So the first interval is for all real numbers. In that case, let's talk about this generally. This is a opens down parabola because this is negative. So it looks like this. So this, since the domain is all real numbers, it is not going to have a minimum. So no minimum. I don't need to graph that to know it. It does not have a minimum. And the maximum value will in fact be the vertex, specifically the y-coordinate of the vertex. Okay. So I'll need to find the vertex. And now I know that because if I'm looking at the entire domain, then over the entire domain, the biggest value is the vertex. Okay. Now what can happen though is that if we have a truncated domain, so if we just look at this interval 10 to 20, it might happen that the function does something like this, but we only look at, say, like this portion right here. And so our maximum and minimum will just be taken from this area. So let's see if that's actually the case just by graphing it from from 10 to 20. Do zoom fit. All right, so this is a good example. So the minimum is just going to be the leftmost value and the maximum is going to be the rightmost value. So since the leftmost value is 10, the minimum the minimum will be, in fact, just y1 at 10. So that's my minimum, 171.88. And my maximum, again, from the graph, is just going to be the value of the function at the rightmost x value, which is 20. And so that will be the function evaluated at 20. And that's going to be my maximum, 194.58. Now, if we look at 20 to 40, again, we've got to graph it and see what interval we're working with here. So I'll do zoom fit with that again. And from 20 to 40, I actually see the vertex. So that answers one question. The vertex, the maximum from 20 to 40 is going to be the y-coordinate of the vertex, which we've already found. So for that, to get that, we would do calc max. The minimum in this case is actually going to be the leftmost endpoint, which is going to be y1 at 20. So it's kind of funny because in here, y1 of 20 was my max, but here, y1 of 20 will be my min. So that's just to give you an idea of how these things can change depending on what interval you're looking at. All right, So we're going to move now into a new example, and this is a really important example in the world of modeling and physics, and it's that of projectile motion. So basically this is about understanding what happens when you throw stuff up in the air and then it comes down and hopefully doesn't hit you. So suppose a projectile of any sort, ball, bullet, bowling ball, whatever it is, piano, is thrown or fired vertically at time t equals 0 from an initial height of h sub 0 feet near the surface of the Earth. So that kind of matters. If we're not on the surface of the Earth, then things can be different. But anyway, if the projectile's initial velocity is v sub 0 feet per second, then its height h in feet after t seconds is given by the following model. H of t equals negative 16 t squared plus v sub 0 t, that's the initial velocity, plus h sub 0, so that's the initial height. So this is a quadratic function. It's a negative leading coefficient, therefore a downwards facing quadratic function. And basically what it's telling you is that if you have time on this axis and height on this axis, that at time 0 you'll be at your initial height, and then you'll either do this, so you'll be at these heights as time elapses, or you'll do that, or any kind of arrangement of this sort, which is a portion of a quadratic, and then at some point you'll hit the ground. Well, not you, but whatever it is you threw. And that's going to be the kind of the end of your domain. Okay. This negative 16 number, that has to do with the gravitational field on the surface of the Earth. This would be different if you were on a different planet, or if you were very far away from the surface of the Earth. Okay, and another word about this model. So h sub 0 is your initial height. V sub 0 is the initial velocity. But you need to understand a little bit more about initial velocity. Initial velocity can be positive, can be negative, and it can also be 0. And we need to be able to identify what scenario we're in, and it's pretty easy to do this. Basically, a positive initial velocity is when the object is thrown upwards. A negative initial velocity is when it's thrown downwards, kind of hurled downwards. And 0 is when it's just dropped. So if you just like open your hands and let the object fall, but you don't throw it down, then you have 0 initial velocity. And that will change your model. Okay, so here's an example. A ball is thrown vertically upwards from a height of 5 feet above the ground at a speed of 70 feet per second. Find a model that gives the height of the ball, h, in feet as a function of elapsed time t since it was thrown in seconds. So we have vertically upward, so we have a positive v sub 0. And what is that v sub 0? It's 70 feet. So v sub 0 is going to be 70. My h sub 0 is going to be 5, so that's h sub 0. So my model, my h of t model, will be negative 16 t squared plus 70 t plus 5. Okay. And I'm going to go ahead and enter that in the calculator. Okay, so I've entered this in the calculator, and I'm going to graph this. Now remember that when we have a function like this, it's going to look something like this. Okay. I don't care generally about the domain outside of this point of impact, which is a 0. So basically what I want to do is I want to go ahead and just look at the graph of this, but I'm going to look for my table and see when this becomes negative. So you notice this is negative at 5. So I basically don't, that's 5 seconds. So basically I don't need to look at anything past 5, even like somewhere between that, but I'll put 5 in and then do zoom fit. Okay, so this is a good picture of the function. All right. Now I just talked about a little bit about velocity, a little more about that. There we actually have two quantities. We have velocity and speed. Velocity has both magnitude, but it also has direction, so it can be positive, negative, or 0, like we talked about. Speed is the absolute value of the velocity, so it's always positive. So your speed can be 30 miles per hour, but I could be going 30 miles per hour up or 30 miles per hour down, but my speed would be 30 miles per hour. My velocity, though, is different. So we talked about how this looks in terms of velocity and projectile motion. So for direction, and now let's go ahead to using the model. So when will the ball be at a height of 50 feet? So 50 feet is an output, so that's going to be my y2, and I'm going to do a calc intersect here. So there's 50. Oh, and I just screwed up, didn't I? That was negative 16, sorry. There's my 50. Now let's graph that. And we have 2 points. We have a point here and a point here when we're going to be at a height of 50. So a height, basically an ascending and descending. Okay, so that's calc intersect, and when that means we actually have to do calc intersect twice. First curve, second curve. Just to save me a little bit of time here, I'm going to go to the one that's closest. And I actually need to move my cursor over here to help the calculator know which one I'm talking about. And there we go, there's that intersection, so 3.59. That's the one coming down, the descent. Now to find the other one, we need to do calc intersect again and move your cursor over here for your guess so you can actually get a different value. And so then we'll find 2 of them. I'm not going to do the other one though, you can do that on your own. What about question B? When will the ball reach its maximum height? Okay, so the maximum height is a calc max question. And what will be the ball's maximum height? That's also basically another calc max question. This is just essentially the x coordinate and the y coordinate of the maximum point. So to answer both of those, we just need to go to calc maximum and move your cursor. My picture kind of sucks because it's hard to see where I am, but in fact I don't think I did a good job. I think I need to go bigger. See, I just gave myself a little bit more headroom there so I could actually see. Also, I'm going to delete this 50 because that's confusing me. Now I can actually see the maximum and calculate it. Okay, left bound, right bound, and my guess. And there we go. There is our maximum. So 2.19 is the answer for C, and I'm sorry, for B, and 81.56 is the answer for C. All right, we will do D and E in the next video.